Okay, so first of all, I want to welcome everyone on the seminar. So today is 6th, and this is our fluid mechanics seminar. This is gonna be early UG fluid mechanics, and we're gonna build up from basic high school level. We're gonna be using some calculus, and we're gonna learn some calculus and some things which are used in higher fluid mechanics. Even if we don't use them, I think it's really important to know about them. So we're gonna study each and everything step by step. So the things we'll be covering in this seminar are gonna be the Euler's equations. It's actually a single equation. So that's the Euler equation, and we're gonna look at mass conservation. We are also gonna look at the stress tensor in the Kronecker Delta function. The stress tensor, we will be looking at it in depth, not in too much depth, but we won't be using it to actually in equations because that will require some of its own maths, which not gonna be able to aggregate in a single seminar. And then we're gonna derive the Poisseuille's formula or Poisseuille's law, which is a very basic question that's asked in fluid mechanics, and it's really interesting that how pressure is related to the volumetric flow and the velocity of the flow in a cylinder. And we're also going to be using viscosity in the Poisseuille's formula. So that's how you can know how viscosity is used basic forms in fluid mechanics. Also, we're not going to look at momentum conservation because we will be applying some of its own maths, more some more advanced things like Hooke's law and stress tensors or transformations to actually figure out momentum conservation. Momentum conservation is also famously known as not the Navier-Stokes equations. So we're gonna skip that for now. But everything else is also gonna be interesting. So I'm gonna move ahead. I'm gonna check up on pugs. Okay. So first of all, let's jump to Euler's equations. So as in any mechanics class, we're gonna be just looking at forces on an object, on an element, on any object, and then we're gonna just use basic F equals ma Newton laws to derive equations and predict its mechanics. So that's what we're gonna do here. Nothing too fancy. So we have a fluid element that's of with ds. We have taken an infinitesimal fluid element. I hope it's clear. It's the arrow showing a length, and it's ds. So first of all, we're gonna derive the Euler's equation. It's ideal fluid flow. So we're gonna just lay out our assumptions for what we're gonna assume and what we're gonna put in our equations. So the first assumption is gonna be the fluid is incompressible, and it's homogeneous. What this means is density will not change. If you look at a patch of fluid over time, then the density will not change. So that's really important because if density changes, then we have to take in more factors, and we have to model the density that's flowing inwards and flowing outwards. And the fluid is going to be non-viscous, which we are also gonna ignore viscosity here. Flow is going to be steady and continuous flow along the streamline. And the important thing here is the word steady. Steady means if you look at a patch of fluid, then it won't experience acceleration at that point. Basically, the derivative velocity with respect to time is not going to change for that patch. That what steady means. So we're going to go forward and we're going to label our forces. There are going to be three forces. The first force is going to be force due to pressure. That's gonna drive the fluid in our fluid element. That's gonna be the pressure times the area. I hope that's really clear. Also, we have we have labeled the cross section area of the cylinder as dA. So the force that's going to be at the start is going to be rho dA. Now we're going to move ds times above. That's ds times above. So to move ds times above, we're going to add something to the initial force that's at the bottom, because it'll be lower at bottom, will be higher at top. I hope that's intuitive. So we're gonna first of all we're gonna find the change of pressure with respect to our width, like how the pressure is changing as you go upwards. We're gonna find that, and as we're working in multidimensional, we're gonna go multidimensional. We are gonna be using partial derivatives. So the way our pressure change times, we're gonna add that ds times, because we have the change of pressure of the pressure with respect to the cylindrical's width, and then we have to go ds times above. So like the partial of rho with respect to the width, and then we have to like add it ds times. So we go up ds times. That's why we multiply it by ds. Or you can also derive this from basic unitary method, which is really into it. And then we're gonna multiply it by the area. So we get the force, not the pressure. And now we're gonna take in consideration of the gravity. So we're gonna think of this now as a simple block on ramp problem. That psi is the density. So we're gonna just label mg. The vector is gonna go vertically down. We're gonna break m into density times the width times the area, and then we're gonna multiply it by g, mg. That's the force due to gravity. And as we know, we have the angle theta here, the vector of the weight that's along the line which we are working with is going to be mg cos theta. So psi times ds times dA times g times cos theta is going to be our force, and it's going to be in the direction of the bigger pressure force. That's going to be rho plus the derivative of rho with respect to s times ds times dA. Check up on pugs once again. Psi is the density of our fluid element. I hope we have labeled the forces correctly, and everyone's understanding how we're labeling the forces and how we're working on it. Now everything is done. The free body diagram is done. All we need to do is just write our equations. So bear with me. This is the first equation. This is nothing. Don't be scared. This is gonna be our first force. That's gonna be rho times dA. Then we subtract the other force because the vectors are opposite. So we're gonna subtract the first pressure force from the second pressure force. That's gonna give us the net pressure force, and then the the, the force due to the weight. It's gonna be mg cos theta. We're gonna write that and subtract that because the direction of mg is along it's downwards, right? So that's why we're going to subtract it. So that's all. That's the equation. That's nothing fancy. We just derive stuff, and we just label the forces, and then we just use basic F equals ma. Now the right hand side is the same. The right hand side is the same. The left hand side is going to just change to the mass times the acceleration. And as you can see, we have labeled mass as the density times the area times the width of the cylinder. And nothing else is changed. Now I'm going to include a hell box here for you. That's the chain rule for going in for partial derivatives. So we have z as a function of x, z as a function of x, and x and y are functions of t. So we can break the derivative of z with respect to t as follows. I hope that's clear. That's calculus 3, by the way. So I've put a hell box for you. So that's how we're gonna break our acceleration. Why are we breaking our acceleration into partial terms? Because we have partial terms on the other side, and we're gonna cancel them. We don't want to make it a partial differential equation. We just partial differential equation. We just want to we just want to eliminate the partial terms on the left hand side. So we're gonna make our acceleration in partial terms. And now what we're gonna do is we're gonna add a rate that's going ds downwards, and we're gonna model cos theta from basic trigonometric ratios. That's gonna be ds upon dz upon ds. That's we're gonna put cos theta as this as other dimensions, so we don't have to evaluate cos theta at a higher level when we evaluate the equation. We're gonna put we're gonna put cos theta as dz upon ds, and we're gonna just replace acceleration with what we got. Change here for everyone. We are Flynn. We are calculating. We are just looking at forces on a fluid element due to pressure, and then we're just using F equals ma on it. Rho is our pressure and psi is our density. Yep, exactly, bugs. So just work out with me. Work out with me. We replace the acceleration with what we used chain rule upon. We just used the chain rule on dv with respect to on our acceleration, and we got this the third equation, and we just placed a with that, and everything else is just the same. Nothing's changed. And we also replaced cos theta with dz upon ds because that's basic trigonometric ratios. We just don't want to work with theta. We just want everything to be in the terms of what we have already in the equation. So dz upon ds is very convenient. Now here comes the tricky part, the most tricky part, which I want you to pay attention to it. So there is acceleration on the fluid element because there's pressure, there's force, and there is an acceleration. But we are working with a steady flow. We're working with a steady flow. If you look at it from higher dimensions, velocity is not going to change if you look at a patch of fluid with respect to time uh, of a single fluid parcel. You use the word parcel in fluid mechanics. So if the velocity was changing, then this won't be really ideal. Then we would have another term in our equation which we have to work out to work changing acceleration. Then fluid would go haywire, and we might have some sort of non-ideal fluid movements which we cannot model with just our single dimensional differential equations. We're gonna assume this is steady fluid. So the derivative of velocity with respect to time is non-zero, but the partial of v of velocity with respect to time is zero. So we're gonna cancel that term. I hope everything clear yet again. I'm gonna repeat it again. Go back. Go back. The overall fluid has an acceleration because it's driven by pressure, and there's pressure, there's force, there's acceleration. We are clear here. But if you look at a fluid particle, like the whole fluid element in higher dimension, in a higher dimension, and then you see its velocity with respect to time. If you just like, the meaning of steady flow is basically you just don't see a fluid changing its velocity with respect to time when it goes in a streamlined fluid. The driving force is going to be non-zero because that's what makes that's what keeps the fluid flowing. But if you look at the individual particles, its velocity is not going to change if you it higher than it. I hope that's clear because this is a really tricky part. But basically, when we look at the fluid when we take the change of fluid like in most dimensions. So, for example, if you work out a partial of anything, then you're gonna be working in taking consideration of the change in more direction. I'm oversimplifying it, but I don't know how else to make it really intuitive. I really want you to go into the mathy details, which you can research, which you can really get easily on Google. So with this, we have literally nothing more left. We're gonna assume the steady flow, and we're gonna make that zero, and the rest is just boring mathy algebra. And we're gonna just take the sums on the left and the right, and then gonna subtract, and we're gonna add them, and we're gonna arrive at this equation. So the next part is trivial. Nothing, everything is done, and we literally just derive Euler's equation. And the fun fact here is if you just integrate this equation out of nowhere, just integrate this, you're gonna arrive at Bernoulli's equation. So that's really interesting. And we know Bernoulli's equations. Bernoulli's equation is derived from basic energy conservation or an invoke energy theorem, which we look at the fluid we look at the fluid from height h above, and then we work out potential and we work out all the energies, and then we arrive at a relation. You're gonna arrive at the same relation if you just integrate this equation out of nowhere. This is Keynote. It's really really great max stuff. So let's move forward. I hope everything is clear, and I'm making like it's if there's any other questions, then I really really want you to ask it now because we're gonna move further. We have done with Euler's equations. I'm gonna assume no one has any more questions. So what we learned from that? Why did we even derive Euler's equation? So it's a good start for diving into fluid mechanics. We learn how to look at fluids in fluid mechanics and how to form equations because it's really simple. It's just basic dynamics. We just use F equals ma, and we model forces. We make a free body diagram, and we just take in every force, and we just work out equations. Intuition for working with control volumes, that you can also call the fluid element as a control volume. That we work upon is the control volume. And how to apply assumptions to our equations. If it's a steady flow, then the partial of velocity with respect to time is going to be zero. So we apply an assumption to our equation. Also, we apply the incompressible part to our equation by just throwing in psi. If we just okay, let me go back. We just threw psi in there like it's nothing because it's like it doesn't make sense to throw psi in there because it's gonna change after some time, and because we have time at the left hand side, because we have acceleration as time acceleration, that's dv by dt, and psi it's gonna be different after some time. So that's how we apply the incompressible part to our equation. I hope it's clear. Okay, so we're gonna move on to mass conservation. We're gonna do things. We're gonna move really, really slow here. So first of all, we're going to establish one thing that that's gonna allow us to go forward. The net influx of mass, or the rate of mass flow, is going to be equal to the rate of increase of mass. Or you can say the total mass is going to be the mass that came in times the change in mass. The net influx of mass is going to be the rate of increase of mass. I really want you to give attention to this part of of mass conservation, because this is what really gonna allow us to derive expression for mass conservation. I hope it's really clear what the relation means. It's gonna come to you as a theorem if you look at it in a fluid mechanics class. But if it hadn't been a fluid mechanics class, I would have been going things in much deeper, in much deeper sense, and much deeper and much more lower pace. But I'm really going really fast. So the cube here is our control volume. What we're gonna do is we're gonna look at the fluid that's coming in from one direction, and then we're gonna look at the fluid that's going out in the other direction. Basically, the mass that's gonna come in and the mass that's gonna come out. And we're not gonna look at only mass. We're gonna look at the mass flow rate, which is the mass times velocity, which we establish the rate of mass flow, which is the net influx of mass. The rate of mass flow is going to be the mass times velocity. We're going to break mass. We're gonna just break mass into density times dy times dz. We're gonna ignore the other parameters because they're not gonna change. Basically, the dy is not gonna change. The dz is not gonna change. So we just gonna leave at the area part clear. And then we're gonna look at mass that's coming outside. Now here we just took dy dz on the outside, and we're gonna add like what we did in with Euler's equation. We're gonna do the same here. We're gonna be seeing the change in the density in density times velocity, because that's what's gonna change, right? If you go from the right from the left face to the right face, what we're gonna see is density change, and what we're gonna see is velocity change. So we're gonna see the change with respect to x because we're working in x direction, and then we're gonna add the x times because that's how far we are going, the x times, and then times our dy. So that's the whole mass flow rate. Now, this is completely unrelated to our mass equation, and it's really simple. The rate of change of mass is going to be the rate of change of density with respect to time, with respect to the part, with respect to time. I'm sorry, with respect to time times dx times dz times dy. This is really simple. We're going to write mass in terms of density because we are working in terms of density. What we did with Euler's is the same. We just wrote acceleration in partial terms because we had partial term. We're gonna write mass in terms of density. Psi is still density, rho is still pressure throughout the seminar. I hope that's clear. So we know how our mass change with respect to time. That's going to be equal to the net influx of mass all directions, which is what we established at think of mass conservation. Uh, I'm gonna answer your question later on. Right now in mass conservation, I'm gonna answer it for sure. I really want you to Google steady flow, or just basically just Google the words buzzwords. They really tell you. Just go Wikipedia. They really tell you what exactly I'm saying. So nothing major here. We looked at some fluid that's going inside. We looked at some fluid that's going outside, and then we're just gonna subtract both terms because that's the delta mass. That's the change in mass, right? That's the mass that's gonna come in. That's gonna go up. The mass remaining is gonna be the net negative of that, and that's gonna be equal to how our mass is changing with respect to time in the control volume. I hope that it makes sense now. So we model our forces, we break mass in, in density, and we find the net influx of mass. So the first term, that's gonna be the left side minus the right side. It's gonna give us that delta M in the control volume. And that's gonna be this. That's just for the X direction because we have our change of density, and then we have dx, dy, dz. We're going to work out in dx, dy, dz, the change of mass. That's just for the x direction. We're going to have the same for y direction. We're going to have the same for z direction. So it's nothing really complicated. We're going to just do this same thing for our y direction. We're going to do the same for our z direction. I hope it's clear. And so the first time we subtracted the net mass, and we're gonna add the the second dimension mass and the third dimension mass change. I mean, yeah. This is okay. Good question. If you have questions, feel free to ask on whiteboard. I'll be checking periodically what's going on. So as we have our density, as we have our mass, we have our equation, we have all of our masses changes set up for all direction. We're gonna do nothing more than just basic algebra. We're gonna cut terms that are subtracting. We're gonna evaluate. We're gonna open the brackets, and we're gonna just subtract things, and we're gonna arrive at this equation. I really encourage you to take a screenshot and try solving this equation. Anyone can solve this equation. You don't have to do anything. Just evaluate the terms. I encourage everyone to take screenshots here. And I hope the terms are really clear. The W here is the velocity in the y direction, and M here is velocity in z direction. Velocities are not going to be same for every direction. We cannot assume that. But we don't have to really care about them because eventually they're going to cut from our equation. So here we have final expression that's just going to be this evaluated. And now here comes a dose of vector calculus. That's going to be divergence. This is really basic. This, even if you don't know vector calculus, you must know this. This is divergence. Divergence. That's the partial derivatives in each dimension, and we sum them up. I'm not going to go into the intuitive definition of this right now. So for the first expression, we're just gonna move our terms to the left hand side, and that's gonna change the sign. That's gonna be equal to 0. And as you can see, we have the divergence of psi times v here. We just model our velocity as v here, capital. So whenever you open up it, when you open the divergence, v with respect to x, if the density is constant, then v with respect to x is going to be the velocity that's going to change in x direction, then y direction, then z direction. So I just wrote it as capital V, so you can conclude up here what I'm referring to here. So that's mass conservation. This famous equation is what we see above Navier-Stokes equation. We just derived it so easily. And so that's how we drive the Canadian equation. It's nothing complicated. It's really, really simple. just look at masses that's coming in, going out, establish theorems, and then write equation, evaluate them. That's how you got mass equation or the continuity equation, as Silent mentioned. So now you're gonna go next. Tensors, yeah, tensors. That's really interesting. Now I'm gonna go really oversimplify tensors for you because they're intuitive, but I'm gonna make them I'm gonna make them more intuitive so we're not gonna work with them. So we're just gonna learn about tensors. It's really interesting. They're used in fluid mechanics. So it's worth mentioning. Tensors, think of it like vectors. Rank 0 tensor, a rank 0 tensor is scalar, and then you go higher ranks. That's rank 1. That's a vector, and then rank 2 is what we call tensor. So vectors are just arrays. It's also a matrix. Vector is also a matrix, but we have different representations for it. We use tensors, but we use vectors, and we just have a single column. We have tensors, we have 3 more columns. So there are 9 elements total. So we're just telling about something in more detail. That's just basically tensors. And then there are some transformations that applies to vectors, and then there are transformations that applies to tensors. So it's just vectors, but more dimensions, more information. We're telling more in a single matrix. That is a tensor for you right now, but that's not exactly a tensor. We're gonna tend the real definition for tensors is gonna be more complicated. So I'm gonna make this as intuitive as I can right now. So these are tensors for you. We're gonna establish a notation. What is y(x), xy, and xy? Why is it there? Stress is force per unit area. We know that. So we're gonna be telling the direction normal vector of area that it's related to area. So we're gonna tell the direction normal vector with the first indice of the tensor T, and the second indice is indice. I don't know how to call it. I'm so sorry. The direction of the force due to stress. Force due to stress. It's still it's still gonna be telling the direction. So we're telling more information in less words. So think of it like a tensor. I know everyone's excited. So let's go forward. So this is basically a cube. Think of it as a cube top. We have our coordinate system here, y, z, and x. We're gonna do a simple activity. We're gonna label tensors here. So we are at the y normal. We are at the y phase. So we are at the y phase. So that's the y normal. I'm gonna think of it as a y normal. And then that's the t by y, because the force, the normal is at the y direction, and the force due to stress tensor, the r vector is going to be in the y direction too. So as you can see, the 3 arrows, it's like a vector, like, so it's like a vector but for a single phase, and then there are vectors for every phase. So that's a tensor. So there are vectors for every phase. So one phase, the front, the back, the left, the side. These are vectors, and these are aggregated together to make a tensor. That should make it more intuitive. Then that's the y(x), because we are still in the y normal, but it's going in the x direction, the direction. So that's the force, it's in the x direction. And then z, you have z here. So you can see, if this was just a vector, you would just like do a cap, b cap, c cap, and you were done with it. That's basically a cap, b cap, c cap, but for every face on a cube. Whenever you do tensors, whenever you're gonna do tensor, I'm 100% sure you're gonna be looking at the stress tensor at the first glance, because that's how they basically introduce tensors in every course. It may be different for other courses, but the one I took a year ago told me how to start the tensors with stress tensor. So that's single face. There's gonna be more faces, and that's how we arrive at this big of matrix. It's nothing. It's really nothing. It's just really simple. Now we're gonna establish. We're gonna be needing we're gonna be needing something. We're gonna needing something vectory from this because we haven't established anything how we work with tensors. We haven't established how to do the communicative properties of it, like how it adds up, how it multiplies, how it forms, how it goes in equations, what we do for any other new quantity. So we're gonna still work with vectors. So we define this. That's is the force per unit area. Is also called the stress vector. That's gonna be the normal times the tensor. That's literally it. That's the force. That's the stress vector. That's a normal for that direction. You get the t there. Or t. That's the dot product, by the way. Some if you label every vector, you're gonna see there are some vectors that are just telling the same thing. So we just cut them out. You just really need to no, we're not doing anything transformations, Vandal. We're not gonna do anything transformation. We don't need to tell if the matrix is symmetric because we're not gonna do any operations on it. We don't need to do anything else about the matrix. Just that how we use it in fluid mechanics is what I'm gonna tell you. I don't want to make it complicated for anyone who doesn't know tensor calculus. Yep. Hope there are no more questions. I don't know that leave any question. Matrix. Okay. Alert. Matrices and tensors are not the same. They are different. We represent tensors with matrices, but you cannot just tell that every single matrix is a tensor. That's wrong. Not every single matrix is a tensor. You need to keep that in mind. We just represent tensors like this way. We also represent vectors in a non-matrix way, which we already know, I cap, j cap, k cap thingy, but we also represent matrices. Let's go forward. So now we have the tensor distribution for a cube for any surface. It's really easy to calculate the net force that's due to the stress for that thing, because we just know the stresses which are going to be on that object. We know the force per unit area for every face. We know everything. We know forces. We know the net force. So that's the net force is gonna be for a surface S is gonna be the stress vector times the dz for a surface. That's a surface integral. So that's the area. I hope that's what we call surface. And it's a surface integral. That's why there's an S. So don't be don't be really scared. It's just notation. So we're gonna establish our net force because we need forces, right? F equals ma, right? Mechanics. Yeah. So remember we're like back in like the very first physics class, where we learn about integrals. It also means sum over every infinitesimal sum over everything that's in the integrand. But we also gonna use that thing, the thought here. We're just adding every stress vector on every surface along the surface or every surface. That's gonna be the surface integral. That's why we have a surface integral and with respect to the S, so the surface. And as we have established before, that's gonna be the normal times the stress tensor. It is. Nothing else has been changed. and we go forward. And here we have some more vector calculus for you. That's the divergence theorem. Now, this is really easy to know. I've simplified it. I haven't included multiple integrals because there are multiple integrals here, but we don't need them because it's really inconvenient to just represent them with a single integral. Velocity, so that's not velocity, that's volume. The divergence of anything basically of with respect to volume along a volume integral of along a volume is going to be equal to the normal times that anything along the surface. That's the divergence theorem. The, I'm not gonna go into derivation for this. It's really famous theorem that's taught in vector calculus. I want you all to look at it. Just Google it. Go ham. And we have our divergence of stress tensor in the integrand, but we cannot go any like how we can go further from it. We're not gonna evaluate the partial for every element, and we're not gonna go anywhere because that's so we need to find the meaning of the integrand. Before stress tensor, we arrive at the mass conservation. So what we did for mass conservation is the same thing which we are gonna do for stresses. So we arrive at divergence because we saw how masses are coming from one side and another side, and we used theorems on it to relate the change in mass, and we got divergence just because we got divergence. So we're gonna use this. We can do literally the same thing for the stresses on an object because we know how stresses are there on an object, how they're distributed, how they're labeled, and its notation. So we're gonna just use that, and we're gonna look at them same way we look at mass. And how we're gonna relate it? We have no theorems. We have no theorems because we had a theorem for today. The mass that's gonna come in, that's gonna go out. We had a theorem that's gonna be net influx of mass is gonna be equal to the mass flow rate. Here we have basic forces. So tensor, we're gonna we're gonna just go from the stress. We're gonna go from stress. We're gonna go from stress to force, and from force we're gonna use F equals ma, and then we're gonna aggregate everything, and then we're gonna arrive at a relation. Same. So this is just for x direction. This is gonna be the tensor at the x direction, and then the x normal times dy dz. dy dz is the area of cross section for that cube. So for that, I mean the face. So for that face, the area times the stress tensor at that direction is going to be the force. Stress, yeah. We're gonna do so. It's stress, right? So it's gonna deform it. It's gonna try to deform the thing which is acting on it. So that's why the vectors are opposite. I'm so sorry about the arrows. These are really small. Yeah, I hope you get the direction. Can you tell exactly what part you can't understand? Okay, I'm gonna take some time to answer the questions here. I'm moving too fast. Let's not go there yet. Exactly. Yes, tensor is a field. It's defined for, like Proxy said. No, that's for headshot. I just really want everyone to understand this. We're gonna take all the time we have. if you have any specific question that's related to how is it, then I'm happy to answer it. The physical quantities and everything, so it changes by time. Yes, the forces will change, and there will be reasons for forces to change. There, any reason for the force to change is gonna be an external force that's not gonna be in our system. So let's go back to basic mechanics. Basic, like when the net force is zero, there is no external force. Net external force zero, then there's the net force is zero. Where we're gonna be then how then that's how we're gonna we are gonna assume net force is zero. That's how we're gonna arrive on that later in the seminar. Okay, so I'm gonna repeat that again. We're gonna go back and we're gonna do it again. So we have our stresses that's happening on a phase. We look at a single phase for now. See why I this the force in the stress is going to change only when there's an external force. We're gonna establish that we have no external force later in the go to seminar. We have no external force zero. We have no external force for zero. That's really basic. That's basics of dynamics and mechanics. What's the name? So we're gonna just take our tensor times the area. That's gonna give us force, pressure upon area of force. Sorry, I mean force upon area of pressure. And pressure is force times stress tensor line for that particular direction to the area. So we get the force upwards because it's trying to deform it, right? That's what stresses do. So it's gonna act in opposite direction. And okay, the next slide is horrific. So net force is going to be zero. No external forces. The stress is not going to change because there's net external force. Any questions? I'm moving too fast here. We have no equations right now. I'm sorry about the next slide. You'll have equations now. Now, so this equation. Okay, so look at the first term. Look at the very first term. Txx plus the partial of txs with respect to the partial of x times dx. We establish how we go txx plus the partial of txx with respect to x times dx. We just see the change for how far we go. We multiply it times how far we went, and then we just add it to the initial term. That's dxx dy dz. We took dy dz in common. So the net force is going to be this left expression minus the right expression, which we did. And so this is just for x direction. This whole expression is just for the x direction. If you look at the second term, dyx, the normal is in y direction, but the force is in x direction due to stress. So we're still looking in the x direction for the forces. Yep, exactly. Yep. That's what we did for a change in mass when we moved to see the change in in the dx direction on the dx times forward. That's what we're gonna do. We move dx times forward and we multiply by dx. That's gonna be, so we learned that there are gonna be a whole vector coordinate, a whole like three vectors for a single face. So we're gonna have three expressions for a single direction. That should make sense. So we have tyx, and then the second term, the tyx plus the partial of tyx with respect to y times ty, subtracting the stress that's going to be in the other direction, tyx, and then tzx. After tzx, we are done. We don't have any other forces that's in x direction. We're going to be looking at forces in x direction. So we're going to be in a stress tensor notation is where it is. That's going to be this. Here, y is the direction of force. And we need to find the net force in a direction. So we're going to look at the net force in that direction by looking at the stresses that are in that direction. So though the second indice is going to be x for every stress tensor we use in this equation. And we're going to just be looking at the x direction for this. Imagine if you look at one and y and z at the same time, it's going to be a clusterfuck. So we are gonna have to be careful and work slowly from one dimension and second dimension. The thing here is, if you just work for one dimension for just x, then we will know what will happen in y, because there's nothing is going to change. And then we will know what's going to happen for z, because nothing is going to change there too. We looked at x, we found the net force. We had a tensor distribution. We had a tensor distribution. We looked at tensors for a control volume, and then we looked at the forces in that direction, the net force in that direction. To look at the net force in that direction, we have to consider every force that's there. Every force that's there is going to be the second indices. That's going to be the second indice. That's going to be the direction of force with the stress and the stress. That's, I hope it's really intuitive. Ask as many questions as you want, please. I just want to make it clear to everyone. Lots of people. You're sure. Don't hesitate for taking screenshots. I'm gonna give everyone. I'm gonna make the slide available to you right after the seminar. It's a doc key file. If you cannot run the key file, I'm gonna give you a PDF. If you cannot, if you can always run the PDF. I'm also gonna give you a PowerPoint slide. Code it as PDF. Yeah. So we just, yeah, last slides. This. And basic algebra, we have to cut terms and you arrive at this. Basic algebra, nothing fancy. Just open the brackets and cut the terms. It's trivial, and I'm not gonna waste my time here to do that. We have more better things to do. So f net x is gonna be the partial of txx with respect to x, and you can already see this is familiar. This is what we wanted. We wanted the divergence of the tensor. We are successful. We know what we have an equation that's relating the divergence of the tensor with the net force in x direction. So we know what the divergence means. So that's dx, dy, dz is going to be the area. We're going to divide the area. So we're going to get f net x upon area. That's going to be the divergence of t. Now, this is going to be same for y. This is going to be same for z. We're going to go up, and we're finding the f net total for the every direction for for every direction, and the whole area. That's going to give us the same thing. It's going to give us the differences of the whole tensor. It's going to end up in a matrix. Dxy will change. We have no external force. So force is going to. So we found the net force. We know the differences of tensor is going to be the net force per unit area. That's really, really great. We know what's the differences of the stress tensor, which is gonna that's gonna be the net force per unit area. I hope this equation makes sense because we have, if you look at it, you do analysis on it, you'll be earning a force. If you want to make sure from that, the components for the stress tensor are here. No, this is not a lecture. This is a seminar on fluid mechanics. For F, okay, for net force in Z and net force in Y. So that's gonna be okay. That's gonna be Tx Ty plus for Y Tx Ty plus the partial of Txy with respect to x times dx minus Txy times dy dz, so on for the second term, so on for the third term. Yep, this is it. Now we know what's the derivatives of the stress tensor. We know, so we can actually make sense of this equation now. It's just going to be net force. It's that simple. So that's how we're going to use tensors in fluid mechanics. We all know net force is really, really important here. We're going to use this equation to derive Navier strokes later on. But we're not going to derive it here. That's going to be too long and too much explanation to do. Now we're going to look at the Kronecker Delta. That's also something which we use in fluid mechanics. It's really simple. That's going to be just 2 slides. This thing has 2 indices, and this whole thing is just 0 when the indices don't match, and it's 1 if the indices match. It's that simple. If you have delta 1, that's the delta basically 1, 2. 1 and 2 are not equal, so delta 1, 2 is going to be 0. If you have delta 1, 1, delta 2, 2, delta 3, 3, delta x, x, anything, I and the both indices are matching, that means the expression is going to be, the delta is going to be equal to 1. And we're going to use it in our expressions to do things like this. For example, a tensor, for example, anything that has indices vi times delta ij is going to give us either 0 or is going to give us vi, right? If had been there and in indice, that's for example here, then we're going to establish that I and j and k, so they both have to be 1. I and j are going to be equal, j and k are going to be equal. If they're not equal, 0. That's the Kronecker delta. That's basically it. I really wanted to tell you how to use this in real life, but it's really complicated. If I could have been, if I had been tried to compress this whole derivation in a single seminar, I wouldn't be able to do it. But I would really love you to show it anytime. You can just ping me here. That's a Kronecker. That's the end of Kronecker Delta. I would have loved to show you how we use it. Now we are gonna arrive at the final equation derivation. That's gonna be Poisseuille's formula, Poisseuille's law. So a quick glance over fluid mechanics is going to be over just after we derive Poisseuille's equation. So we have mass conservation, we have fluid flow, ideal fluid flow equations, and we also have stresses and stresses, and we know the net force. A question that can be as basic that can be as basic as it can get, that can be asked to the whole fluid mechanics community can be, if there's simple simple pipe, like a simple pipe, simple cylindrical pipe, and water is flowing through it. Water is simply just flowing through it. It's going by its day, it's flowing through it. And what is going to be the relation between the pressure, the velocity, the volumetric flow rate for the whole fluid? What's it going to be? It's a good question. It's a really good question. It makes you think. It's a simple thing. The pressure distribution, the velocity distribution, the volumetric flow rate in in a pipe, in your arteries, in your blood capillaries. How blood and blood's pressure relates to how it flows, how much volume is there, what's the radius of the cylinder, and how it works. How are we going to take viscosity in term? We're going to take viscosity in term right now, and how viscosity changes it. So that's really interesting to look at, and we're going to look at exactly that scope. So where exactly? No, no, no. V is not velocity. V is just a variable here. Slide. Yep. The delta matrix is just something which is basically it's think of it as a transformation. Think of it as think of it as something which you multiply in an expression to get something out of. Just force something out of. So, for example, we had delta ij. Just example, we have delta ij. We're gonna need to tell them that I and j are equal. Just throw in another delta jk until it's non-zero. That's gonna automatically give you the idea that i's are equal, j and k are equal. If you look at vectors in tensor notation, the complicated vectors, normal vectors and complicated vectors, the expressions are going to become really, really big. They're really big. And you see the Kronecker delta in there. And that's where it will make complete sense. Why is it even there? What does it even do? I cannot go towards the complicated vectors part because you can express vectors in a very complicated way. But I just want to confuse you a whole lot. This is Einstein's summation notation, which I haven't introduced it yet. If you just do ij, that's just basically just means sum over those indices. You can Google it. It's really famous. The Einstein notation. That that's also a good thing to know. Exactly. So, what's going to be a flow rate? What's going to be any we're going to start at by modeling forces. It's going to be pressure times area. Now we're going to look at the forces that's coming in, the forces that's coming out. So the P1, P2 at any point, you can take any point in the cylinder. Now, as you can already see, our velocity profile for the flow is parabolic. If you zoom in it, it's not exactly parabolic, but we're gonna assume it's parabolic. You can see the velocity at the corner is negligible, and at the middle it's really really fast. That's I hope that's intuitive. That's because there's friction against the wall, because there's wall that's gonna stop it. Oh, by proxy. So fresh force is pressure times A. And the pressure difference times A. The net pressure times the change in pressure times the area. The area is going to be pi r square because it's a cylinder. So r square. Now we know this. This is we even learned this in high school. We are gonna be expressing viscosity in basic gradient terms. So first of all, we're gonna forget there's a mu there. We're gonna forget there's a mu there. We're just gonna be looking at viscosity, the force of viscosity. What's it going? What's the viscosity? And what's it gonna depend upon? How will it depend upon? And from what it will change. So first of all, the area, that's really really easy to understand because there's more area of contact, then it's gonna apply viscous force according to that area. So we're gonna multiply area, and then, for example, if there's viscosity for fluid that's stretching, for that's stretching for some length, and for some length, we're gonna take that infinitesimal length in consideration times the velocity. Why velocity? More the velocity, more the relative motion, and more the force due to viscous fluid. And and how that velocity changes with that small distance where the viscosity is acting upon is gonna tell us the distribution, basically the gradient about how our pressure, how our fluid, how the viscous forces are acting to it, or the partial, PARCE, partial. Now, as you can see, our fluid, so we're gonna see the fluid profile, and as you can see, it's symmetric. We're gonna cut it in half, and we're gonna look at it really, really closely. As you can see, from going from up to top, that's r, that's a radius, and you can see the flow velocity is highest at the top, and the flow velocity is least at the corner. So the velocity that's changing with respect to r, like go down and see how velocity is changing. Like so, start from the point where the velocity is least, and then go down and check the green arrows. That's velocity is changing. It's increasing. It's increasing. It's increasing. Then boom, it's the maximum at the center. So our velocity are if you increase the mass, if I mean the radius, if you go down, the if you go down, the velocities are increasing. That means the force, that's the resistive force, that's our viscosity, is decreasing. So that also tells you why dr is in the bottom. Then dv, velocity, is that's going to depend because the more the velocity, the more relative motion we have. More relative friction is just relative motion, opposing with motion. So yeah, I hope the viscous force equation makes sense. Any questions for this equation? So we're just gonna use the area that's in contact with the water. because that's what I told you at the start. The area on which the fluid acts upon is going to be the area where the force acts upon. So that's the lateral surface area of the cylinder. It's going to be 2 pi RL, which is the lateral surface area of any cylinder. And negative because it's a resistive force, and we have taken our pressure force positive, so we have to take this as negative. That's going to resist the motion of the fluid. That's why we have velocity profile. So what you will see what we're going to do. We have the partial, well, I mean not the partial, I mean the derivative of v with respect to r. We do have a derivative in the force direction, so we're going to be deriving the velocity profile for this instance. You're gonna see you're actually gonna predict where we're gonna go. So net force zero. Net force is gonna be zero. The top equation of V is just what I just copy pasted it the next slide, so we can just see what we're working with there. Net force zero. Force to the pressure is gonna be the force to the viscosity of the fluid. That's just opposing it. That's what's causing the velocity profile. And that's the delta P. That's delta P times pi times r squared. That's the old equation. And we don't have any more zero. Right. So our expression on the left hand side, we're gonna write it to the right hand side. Net for zero and basic algebra. Now we just wrote the term again above. And the second term is gonna be just a rewrite of it. You're gonna have dv on one side. You're gonna have dr on another side. You're gonna take the r term on the other side. So we are at this conclusion. You're gonna integrate it. We're gonna get r squared by 2. And for the first time in history of physics, we're gonna add a plus c, our indefinite integral. I hope this plus c is clear. We just use it because we can find it. We can find it. That's why we add a plus c there. How we can find it? We have to know a condition that's gonna be able to relate the both left hand side and right hand side. When the radius of the cylinder is equal to r. Let's go back. When the radius is r, when we are r times above from the center, the velocity is going to be zero. It's going to be least. It's very clear because it's a parabola. That's at the very corner is going to be zero. So at the very corner is going to be zero. We're gonna see how we're gonna just use v is equal to zero, and then we're gonna use capital R. Capital R is the actual radius of the cylinder, and R is the changing radius. So small r. So we're gonna use capital. The first expression is the capital R square upon the same whole expression plus c, and that's gonna be equal to zero because velocity is zero at that point, at that radius. And we're gonna just do c equals r equation, and we're gonna just put c. We're gonna just we have c. Now we're gonna put c back into this equation, which the bottom equation, because we don't know c, and when we put c back there, that's gonna be our third equation, and we're gonna arrive at this. That's the velocity profile. I hope this makes sense. The velocity profile, pressure change. So we have a question. We use indefinite integral because that's what we mostly do in physics. We just use it really in a less careful way. You assume it's adding infinitesimal terms. So we just because we have infinitesimal terms, so we're gonna just use an integral to just squeeze out the r from it. We're gonna add it infinite times. That's why we use an integral there. For example, if we do the integral of f of just basically pressure with respect to area, mathematically is going to mean something different. Physically is going to mean something different. It's going to tell you you're at that's force. That's going to be the net force, the pressure, net force. We just wrote rho. We just wrote PdA. We just wrote PdA. That's the force, and we included an integral, and we just said that it's a net force. Could be done a different way. You had to assume the condition before. Yep, exactly. We also had to know the condition that's initial and then final. If we known that, we would have put in it. So that's the if an integral of rho times dA, that's just gonna mean the net force. We just use this convention in physics. Integral, that's gonna sum up. Okay, so that's the net force. Okay, we put C there. We arrived at this equation. Now everything we related velocity with pressure with the radius. We need to relate how much we just didn't relate how much fluid is flowing inside and like how much volume is going inside and how much volume is coming outside. We don't know how much fluid is going or coming inside. We just know what its pressure is gonna be when the radius is gonna be this and we it's gonna be pressure and velocity and radius are gonna be that. So we're gonna do is look at the cylinder again, this time from its top, and we're gonna be looking at an infinitesimal area from where the fluid is gonna enter. That's dA, and we're gonna assume the velocity of the fluid parcel is gonna be v. The volumetric flow rate is gonna be v times dA. We're gonna simply integrate both sides, squeeze out q from zq. That's going to be v times dA, and we're going to switch to cylindrical coordinates because we are working with a cylinder, and it's going to be hella like a lot more significantly easier to work with cylindrical coordinates in a cylinder, or else we're going to be using vectors and their components, wasting our time. So we broke our coordinate system into r and dA into r d theta dr. Two integrals because we have two infinitesimal terms, and from zero the integral for r is going from 0 to r because we're going from the center to the edge. So center from the edge, that's going to be from center from the edge, that's going to be 0 to r. At the center there's assume at the center there's the radius is 0, and as you go assume you are at the center and you have covered 0 meters, and then you're gonna go to the edge face of the cylinder, then you're gonna cover r. So from 0 to r. And for the theta, it's a circle. So it's gonna be 2 pi, from 0 to 2 pi. That's the angle in radians, which you're gonna cover. Yeah. Volumetric. So that being said, we know how the velocity is gonna be. We know. Let's just put it in there. So we just put our velocity which we got from previously. We're just gonna put it in there. Nothing else. Just put this in there. And the rest from now is gonna be basic algebra. which I'm gonna do with u. So you can see the r that's outside the bracket. We're gonna take that in. Look at the first expression is the same as the last expression. So the second expression, we took r inside. That's going to be r squared times r minus r cubed. And that's it. That's it. The third equation, we evaluated the integral from 0 to r. We integrated it, and then we just told it's going from 0 to r, and we're going to evaluate it. That's the second expression, r to the power 4 upon 4 times d theta. Now there's nothing theta in here, right? There's no theta in here, but we know it's going from 0 to 2 pi. So that's just going to be 2 pi minus 0. That's 2 pi. Pi minus 0, that's going to be 2 pi. You're going to cut 2 from 4. That's going to equal 8. And we are at that Poisseuille's law. We know how fluid volume, how much fluid volume is coming. We know how much pressure is there. We know how much what's the radius. We know the coefficient for our friction due to viscosity, or the viscous flow. We know everything. We can derive other things from this equation, and this equation is insanely, it's like of really good importance. It's used everywhere. It's used by machines to check blood pressure. It can be used to detect heart attacks. If you have artery blockage, then how much pressure is going to change. You can look at literally the equation right now. If like you have the radius time you raise to the power 4, right? If the radius is going to shrink, even if the radius of your artery is going to shrink half times, that's going to decrease. That's going to, like, the pressure is going to go 1 by 16 times. That's going to, like, 1 by 16. That's 1 by 16. It's going to go haywire. So that's a really, really big change for just going half. If you go 1 by 4, that's 60, but that's like more. So this, maybe question. L is the, yes, 2 pi RL. That's the lattice surface area. L is the length of cylinder. So by this, the seminar, and this is the final equation for Poisseuille's law, and that's how we arrive at it. If you guys want mass conservation to be in there, if you want another seminar, if you like this seminar, then I'm more than welcome to make another keynote for this other seminar for especially for driving Navier strokes or our momentum conservation. If you guys are interested in it. So yeah, that's it. Thanks everyone for attending. It was a great pleasure. Stop now.